So one at a time, let's just cover these. Okay, so your upgrade is going to be on lab 3. You did the upgrade on lab 3, or were you doing the upgrade on lab 3? I forgot. This weekend was lab, okay, no, you did 1 and 2, so you guys are, you're going to have the upgrade test number 3 this weekend. All right, so let's go over this stuff. All right, so these are the same as the lab that you guys did last week. On top of that, it's identical to the conceptual task questions. So what do we have? We got the preference by the military. I'm talking about Navy and Air Force. They usually prefer pilots who can handle high G loads. So they look for people with extremely high G tolerances. So would you expect to see any major differences between the way the bodies of different genders handle high G loads? I'm talking about male versus female. All right, so comparison to average size female to average size male, would you expect to see any differences in the way their bodies handle high G tolerances, high G loads, more like it? All right, once again, guys, none of these questions that I'm giving you is sort of stuff that you can Google. Google is some that you can Google information, you cannot Google understanding. We're not there yet. Okay, technology is not there yet. And what I'm doing is I'm testing your understanding of what's going on during the lectures. It's conceptual problem solving. And check to see if you can actually solve a problem conceptually. This is real physics. We do mathematical problem solving only if the situation renders itself to some kind of mathematical modeling, so you can generate some numeric predictions. Got it? A lot of physics is done conceptually in reality. So the question is, can you handle something like this? So the first thing you need to focus on is, what's a high G tolerance? High G tolerance is, can you stay awake and conscious between 7 to 12 Gs for as long as possible without passing out? Okay, so which means that you have to keep the blood in your body in the right places. It's all about the blood circulation. And immediately you have to focus on a couple of things that women have that men don't. Okay, they must tend to be smaller, so that's a good thing. Actually, it constrains the motion of the blood. On top of that, they got the right amount of fat in the right places. Hips, the breasts, whatnot, so it gets pushed up against the skin. So once again, it constricts the muscles. It constricts the motion of the blood. All right, so they kind of act like natural G suits. On top of that, women can do stuff that men cannot. I'm talking about they're able to deliver, they're able to give birth, obviously. That requires that they should be able to contract their core muscles much better than men can in order to actually push their baby out of their bodies. And so women actually naturally better at handling G loads for the most part. Certain men can do it, but once again, you have to have the right body shape. And you have to have almost bad circulation is what we were going for. You have to be the right size. In general, average size, you would expect the women to be able to do better. And that's the explanation that I was looking for. So how do you answer this question in short? You answer it in short, and you say, basically, you expect the women to be able to do better. All right, it's a circulation thing. Smaller muscles obviously help deter good circulation. On top of that, you got fat deposits pressed up against the skin. So once again, it's going to constrict the motion of the blood. And most importantly, the core strength. Women can handle, they can squeeze and constrict those muscles much better and much more natural than men can. All right, so those are the advantages that women have. So we got the question number 2. So this is an actual incident that took place in 1997. And the airplane ended up getting caught in air turbulence. You know, what happened was the passengers who were not strapped down ended up getting slammed against the ceiling. So the question is, what caused the passengers to rise to the ceiling during the air turbulence? All right, the first weeks, most of you guys came up with some answers. And for the most part, this is a mind twister, but it's not a very complicated mind twister. Some of you guys said, hey, the airplane ended up changing direction. Most passengers retained their initial motion. So most of you guys said something about inertia. Despite the fact that kind of explanation makes sense to you guys, that's not correct, because gravity overcomes your inertia along the vertical direction. So regardless of what your inertia is, how big your mass is, everything is still going to follow at the same rate. If the motion is happening under the influence of gravity, passengers and the airplane will be falling at the same rate out of the sky. So you will only feel weightless. All right, you will not get slammed against the ceiling. All right, projectile motion is the same as free fall, which means that the passengers inside as well as the airplane would be falling at the same rate. It would be perfectly fine. It's like hitting a vacuum. When the airplane is just flying up in the air, everything just drops. Airplane is going to drop. You will drop at the same rate. So you wouldn't have to wear a seatbelt. Some of you guys thought the airplane is heavy, therefore it's going to fall faster. Guys, there's no such thing. There is no such thing. Okay, heavier, lighter, it doesn't matter. It doesn't matter what your weight is. It doesn't matter what your mass is. If you're falling under the influence of gravity, you're falling at the same rate. All right, clearly, what's happening here? The airplane is falling faster than the passengers inside. Passengers inside are falling under the influence of gravity and gravity only. An airplane is not falling under the influence of gravity. It's falling because it's being pushed on by the forces generated within air turbulence, and it's being pushed on at an acceleration greater than the acceleration of gravity. As a result, what happens, the passengers falling under the influence of gravity are falling slower than the airplane. So the ceiling is actually coming down and catching up with the passengers, in essence. So from your perspective, from your vantage point, it's going to look like the passengers are getting slanted against the ceiling. In reality, the airplane is falling faster than passengers on the inside. All right, question number 3.
So I have a question.
Oh, yeah, go ahead. Absolutely. Yeah.
So the passengers are on their place. It's just the airplane is dropping, so that's why the ceiling is coming and hitting on their head. That's what you're saying?
Okay, so Khan, the point that you just made would have gotten you like 1 out of 2 points, because what I said and what you're saying, despite the fact that to you they sound the same, they're not. Passengers are not in their place. That's called inertia. Passengers are falling under the influence of gravity. Passengers are shielded from the effects of air friction. They are going to, at that point, they're going to fall under the influence of gravity. So they're accelerating at a rate which is about 10 meters per second squared, give and take. Except the airplane is accelerating faster than passengers inside. Airplane is not falling under the influence of gravity. It's falling because it's being pushed on at a rate which is larger than the gravitational acceleration. All right. So that's what I was looking for. So give yourself 5 points for actually volunteering yourself and offering your perspective on it, because that was a good one. Because sometimes you guys think that you're saying the same thing. In reality, you guys are not justifying it properly. Either the understanding is missing or the explanation is kind of poor. All right, so this is number 3 is the main observation. The passengers inside the airplane in air turbulence was a leading observation. That was a bit of a mind tease, and this one is a mind twister. All right, the first one was a setup to actually get your mind going in a different direction, and this is a complete sharp left turn. I just wanted to ensure that I wanted to make sure that there was no way for you to actually get to the right answer after that setup. It's a bit of a conditioning. So you got the person inside the elevator. Elevator goes in a free fall. Safety system kicks in, and the person has a broken neck. So the question is, number 1, those of you guys have done a giant drop or Tower of Terror. I don't know what you guys have over at Houston. So we got the 6 Flags here. So you literally, there's an elevator that you walk in, it goes into a free fall at some point. And everyone is safe at the end. Why? Because of the safety system. That's how the elevators are designed. Something bad happens, there's safety system. No one wants anyone to get killed. That's the whole idea. Except in this case, elevator goes in at free fall. Safety system catches the elevator. It's a gentle stop. Yet this guy has a broken neck. So, and most of you guys thought, and majority of the people will believe this, regardless of what happens, that the most likely scenario is the person goes up to the ceiling, gets slammed against the ceiling, and that's how the neck is going to get broken. Most of you guys think that what happens inside the airplane is exactly what happens inside the falling elevator. So my question is, how likely is this scenario? How likely it is that something like this will ever happen? The answer to that question is, this will never happen. How likely is it? Nil, zero, zilch. Why not? Because elevator is falling under the influence of gravity, and the people inside are falling under the influence of gravity. All right, elevator experiences a little bit of air friction, but it's just so incredibly heavy. And the distance fallen is so incredibly short. Even if it's a 500 feet drop, that's nothing. Effects of air friction on the elevator is just zero, negligible. It's virtually a free fall. The person inside, it's completely shielded from the effects of air friction. It's also going to fall at the same rate. All right, so the person is going to remain exactly where the person was at the moment the cable snapped. That's it. The person does not go up. The person does not come down. Center of mass of this person, center of balance of this person is going to remain exactly where the person was. The person will become suspended with respect to the center of mass. So this scenario could never happen. Absolutely not. Yeah, there's a bit of a chance that the person can jump, but not the way you think it is. All right. Just about everything that you're thinking in this scenario is wrong, as you will find out. So the only thing I wanted to know is this scenario even remotely possible to answer that question is no, because it's free fall. For a person to be able to get up to the ceiling, the elevator needs to be falling faster. The elevator cannot fall faster because it's free fall. Weight doesn't matter. Size doesn't matter. Question number 4, once again, we're on the same page. This time, you kind of know the answer, and what's going to happen is, if you lose any points, or if you lost any points, usually the justification is poor. We got 2 bullets. One is dropped. The other one is fired, parallel to the ground. All right, from the identical initial height. So both bullets, one are at the same height. One dropped. The other one is going to be fired parallel to the ground. So which one lands first? The short answer is at the same time. There again, that's it. That's a factual statement. Immediately, you end up getting your 1 point. All right, now you have to justify. The way to justify this is, once again, you have to write it. You don't have some kind of a secret communication system worked out. You have to explain and justify as if the person you're talking to has no idea what you're saying. In reality, if you take this up with someone in real life, at a bar somewhere, you cannot convince anyone that that statement is correct, especially if they don't believe you. So what's the justification for it? You just have to go to the facts. I believe this is the way it is. It's not a proper response. I think this is the way it is. It's not a proper response. I believe this is the way it is. I believe, I feel, I think. I don't care what you believe and what you think and what you feel, guys. This is not about your feelings. This is not about your beliefs. Only things that matter are the facts, the experimental facts. That's it. You state the experimental facts. That's all I'm looking for. What's considered true is what we're interested in. Both of them land at the same time. Why? Ignoring the effects of air friction. What's the only force acting? Gravity. What is gravity? Gravity pulls everything in the downward direction at the same rate. That's it. So the drop bullet and the fire bullet will still fall at the same rate from the same height. So horizontal speed doesn't matter. How fast something is moving horizontally, parallel to the ground, is not going to affect how fast something is going to fall. It's free fall. It's free fall. Free fall is the motion under the influence of gravity. This is the motion under the influence of gravity. So I just provided a full explanation. So the simple answer is both of them are going to fall at the same rate because gravity is the only force acting on them, and gravity makes things fall at the same rate, at a constant rate. So the horizontal motion does not matter. Anything along these lines is going to work. Don't leave anything unsaid. Basically, just cover it, cover it, cover it. It's not your job to convince someone that it's right or wrong. It's your job to provide a full explanation for it. You won't be able to convince anyone that this is correct. The only thing you have to do is these are the facts, and based upon these facts, this is what happens. Go ahead, Khan.
Does the air resistance matter?
And not in this case, it doesn't matter when it comes to bullets because they're relatively heavy. And I mean, it doesn't matter, but you guys have seen the evidence, right? The one which is dropped ended up reaching the ground a fraction of a second sooner. That was 400th of a second. When the Mythbusters did it, it's 400th of a second. It's well within experimental error. The air friction matters because the fire bullet is going to spin. So what is this spin? It generates a little bit of lift. And the fire bullet spends a little bit of a time inside the barrel. All right, so there's some marginal contributions. Outside of those marginal contributions, both of them land at the same time. So it's well within experimental error. Question number 5. Once again, something that we spent a lot of time on. Shooting a monkey from a tree. All right, what would you aim? You know, take a monkey hanging from a tree, right? So we got a slight problem. As soon as you pull the trigger, what's going to happen? The monkey is going to release his grip. If that's the case, where would you aim? At, about, or down below the monkey. All right, so the answer is going to be at the monkey because, again, everything is going to fall at the same rate. It's the same rate of acceleration from the line of sight, because gravity is going to have the same effect on all falling objects. So which means that the bullet and the monkey are going to fall at the same rate. All right, so those are the answers that I was looking for.